examples to see how we can apply or use the fundamental theorem of arithmetic. So this question here says, does for any value of n for a number 4 to the n, the unit digit is 0, where n is a natural number. So if you keep plugging in values of n, and n is always going to be 1, 2, 3 and so on until infinity, because this is a natural number, will you get a number if you keep plugging in values of n that ends with 0? We cannot say that we won't, neither can we say we will, because we will have to keep plugging in values of n until we get a number that is 0 to say yes. But how many values will we plug in? Or maybe let's say if the case is true that the number ends with 0, maybe you have a power, let's say n is 3000, then you are going to have to write 4 or multiply 4 3000 times over to get this number, which is going to be very, very large. Even I think computers wouldn't want to do that. So why should we? But we have a very smart way to do it, which is to use the fundamental theorem of arithmetic to find out whether such a number exists or not. And let's see how we can do it. So if there is a number which is 4 to the n here, and it has to end with 0, then 2 and 5 should be its factors. For example, take 40. So this number I can write it as 4 times 10, and I can further factorize 4 as 2 times 2, 10 as 2 times 5, and even 10 is a number that ends with 0. So if you express 40 in terms of its factors, then it's going to be 2 times 2 times 2 times 5. So 2 and 5 are there, and even the number 10 is going to be 2 times 5, so 2 and 5 are there. And you can take any other number, let's say 30, so it's going to be 2 times 3 times 5. So we have a distinct factor here, which is 3, but 2 and 5 are there. So if you have any number that ends with 0, you are going to have at least 1, 2 and 1, 5 as its factors. And you know that 5 and 2 are primes. And you also know from the fundamental theorem of arithmetic that you can express any number as the product of primes. And if 5 and 2 are primes, and if I want to apply the fundamental theorem of arithmetic to 4 to the n, then 5 and 2 are going to be there, because this number ends with 0, and if it ends with 0, 5 and 2 are going to be there. And if I can write any number as the product of its primes, and 5 and 2 are primes, then 5 and 2 are going to be there. So 5 and 2 are 2 of its prime factors. That means as long as I assume that this number ends with 0, I can always write this number as using the fundamental theorem of arithmetic as 2 times ... maybe there is one more 2, there is one more, or maybe there is a 3, but I'm not sure, but I'm sure there is going to be at least 1 2, then times 5. I'm sure that it is going to be there, because there is a 0 in its unit place. And then there is maybe one more 5, but I'm not sure. I'm sure only about at least 1 5, and maybe some other factors, but I'm not sure, to the n. But if you look at the number 4, and if you again go back to the fundamental theorem of arithmetic, it says you can express any number as the product of primes, but there is only one way to do it. That means I can express 4 as 2 times 2, both numbers prime, or there is only one number which is repeating itself as its primes. So by the fundamental theorem of arithmetic, as long as I use only primes to express these numbers, express any number, then there is only one way to write it. That means I can put it in as 2 times 2. That means I have no other way to express it except this one. That means I'm not going to have a 5 here. And if there is no 5, then I'm not going to have a 0 in its unit place. That means the number is not going to end with 0. Now let's take one more example. And this question is from exercise 1.1, question number 5. And this says, check whether 6 to the n can end with the digit 0 for any natural number n. So if you have a number that has to end with 0, that number here is 6 to the n, then it should have two factors, that is 2 and 5. We do not know about other factors, but 2 and 5 should be there. And 2 and 5, are prime numbers, and by the fundamental theorem of arithmetic, you know that I can express any number as the product of primes. So if I want to express this number, that is 6 to the n, as the product of primes, then I will have 2 and 5 in its product, because these are prime numbers, and I can always express a number as a product of primes, or as the product of primes. So as long as this number 6 to the n has 0 in its end, then this number, and notice here can be written as 2 times 5 times ... to the n. And notice here that I am writing this number only in terms of 2 and 5, because the digit 0 here is enough to tell me that 2 and 5 are going to be there. For now, I'm not focusing on other factors that this number might have, just 2 and 5, because just knowing that there is a 0 in its unit place tells me that 2 and 5 are going to be there. So the product of primes for this number is going to look something like this: 2 times, I don't know, other prime numbers times 5. That's what 1 2 and 1, at least 1 2 and at least 1 5 is going to be there. But now the number 6 can be expressed as 2 times 3 as the product of primes. 2 and 3 are primes, and by the fundamental theorem of arithmetic, you know that you can express a number as the product of primes in a unique way. That means there is only one way to express a number as the product of primes, as long as you are putting it in an order. It's 2 times 3. And if there is only one way, and I know I have already put the number in as the product of primes, that is 2 times 3, that means I cannot really have 5 as its prime factor, which means there is no 5 as a factor of this number, that is 6 to the n. And if there is no 5, then I can say I'm not going to have a 0 at its unit place, because I have to have 2 and 5 as its factors. So any number that is in the form of 6 to the n, or any number we get by putting the values of n in the 6 to the n, that number is never going to end with 0 in its unit place.